When people talk about traveling to the stars, the conversation almost always begins with technology. Better engines, new fuels, smarter designs, as if the universe is just waiting for us to build the right machine. But physics doesn't work that way. Physics doesn't care about our ambition. And the first place interstellar dreams quietly collapse is not in engineering labs, but in the simple, stubborn fact that the speed of light is not a suggestion. It's a wall. We're used to thinking of speed as something you can always increase if you're clever enough. Cars got faster, planes got faster, computers got faster, so it feels natural to assume that spaceships will follow the same story. But that intuition comes from living in a slow world, where everyday speeds are tiny compared to the fundamental limits of nature. Once you step outside that comfort zone, intuition becomes a liar. Light moves at the same speed for everyone. That sounds like a technical detail until you really sit with it. No matter how fast you chase a beam of light, you never catch up. And the universe has arranged itself so that this isn't just a practical difficulty, but a deep structural rule. Space and time themselves adjust to protect that limit. As you go faster, time slows down for you, your length in the direction of motion shrinks, and your resistance to acceleration grows, not because something is pushing back, but because energy and motion are intertwined in a way that makes infinite speed demand infinite energy. This is the part that usually gets glossed over in sci-fi. You don't gradually approach light speed the way you approach the speed limit on a highway. You asymptotically crawl toward it, paying more and more energy for less and less gain. Every additional fraction of speed costs disproportionately more than the last. At 90% of light speed, you're already in trouble. At 99%, you're desperate. At 99.9, you're bankrupt on a cosmic scale. The equations don't care how advanced you are. They don't care how badly you want it. They simply say you can keep paying, but you will never arrive. What makes this unsettling is that the barrier isn't mechanical. There's no wall to smash into. There's no material to reinforce. The limit lives in spacetime itself. It's built into the way cause and effect work. If light didn't have this fixed speed, the order of events could flip. Effects could happen before causes. The universe would lose its logical backbone. So the speed of light isn't just about photons racing through space. It's about preserving the consistency of reality. And this is where the psychological discomfort begins. Because it means the obstacle isn't out there. It's not waiting to be conquered by ingenuity. It's woven into the rules that make the universe intelligible in the first place. We like to imagine progress as an ever-opening door. Physics sometimes reveals something far more humbling, a locked boundary that defines the shape of what's possible. People often respond by saying, "Fine, we'll get close enough." But even that concession carries consequences. At relativistic speeds, energy becomes mass. Your ship grows heavier in the only sense that really matters. It resists acceleration more and more. You're not just moving fast. You're dragging an increasing amount of inertia with you. The universe is essentially charging you interest on speed. And the interest rate skyrockets as you approach the limit. This changes the meaning of travel. In everyday life, distance is something you overcome by moving faster. In the relativistic universe, distance fights back. It becomes a negotiation between energy, time, and reality's tolerance for your ambition. Interstellar space is not merely far away. It is protected by a fundamental speed limit that turns vast distances into near-absolute separations. There's something deeply instructive in this. The speed of light reminds us that not every problem is an engineering problem. Some are boundary problems. They tell us where the edge of the map is. And mistaking a boundary for a challenge doesn't make you bold. It makes you blind. The real power of this insight isn't in crushing dreams, but in redirecting them. If the universe has placed a wall here, it's inviting us to stop trying to run through it and start asking a better question. What are we actually meant to do with the time and reach we've been given? Because once you understand that the speed of light is a wall and not a hurdle, you're left with a choice. Keep fantasizing about breaking the universe's rules, or learn how to live brilliantly within them. Once you accept that the speed of light is a wall rather than a hurdle, a second idea quietly takes center stage, and it's even more unsettling. Suppose, somehow, you do manage to get close to that wall. Suppose you build a ship that can cruise at an absurd fraction of light speed. Physics doesn't stop you from moving that fast. It allows it, but it charges you in a different currency. It charges you in time. Time dilation sounds like a technical curiosity when you first hear about it. Clocks on fast. Moving objects tick more slowly. Fine, interesting, but the real meaning of it doesn't hit until you imagine people inside that moving frame. Because from their point of view, nothing feels wrong. Their hearts beat normally. Their thoughts flow normally. Their lives feel continuous and human. It's only when you compare their clocks to the clocks left behind that the fracture becomes visible. And that fracture is permanent. If you travel fast enough, years for you become decades for the people you left on Earth. Push the speed higher, and those decades turn into centuries. There is no trick here, no loophole. This isn't about bad planning or poor synchronization. It's a consequence of the way spacetime keeps the speed of light constant. Time has to bend so that light doesn't break the rules. And it bends in a way that tears shared experience apart. This is where the romantic idea of interstellar travel starts to fall apart psychologically. We imagine voyages as extended trips, not existential separations. We picture astronauts leaving, exploring, and returning home to tell the story. But near light speed, the concept of coming back loses its meaning. You might return to the same location, but you will not return to the same world. Everyone you knew will be older, if they're alive at all. Institutions will have changed beyond recognition. Languages will have drifted. Cultures will have mutated. Even the problems humanity worries about may no longer resemble the ones you left behind. From the traveler's perspective, the journey was brief. From Earth's perspective, it was an era. And here's the crucial point. This is not a paradox or a glitch. Both perspectives are equally valid. Time does not flow universally. There is no cosmic clock that everyone secretly agrees on. Each world line carries its own version of now. The universe does not privilege reunion. It doesn't care about narrative closure. It simply follows its equations. That realization does something subtle to our imagination. It forces us to confront the fact that interstellar travel at relativistic speeds is not exploration in the human sense. It is exile. You are not extending civilization outward. You are stepping out of it. The faster you go, the more violently you sever yourself from the shared timeline that makes societies possible. Even communication doesn't save you. Signals are limited by the same speed of light. Messages you send home arrive long after the emotional context that inspired them has faded. Replies come back from a world that no longer exists in the way you remember it. Conversations stretch into disjointed historical artifacts. You're not talking to contemporaries, you're exchanging messages with the future. This undermines a very deep assumption we carry without realizing it, that progress means going farther. But human meaning has always been built on synchronization, shared time, shared reference points, the ability to say now. and have it mean roughly the same thing to everyone involved. Relativistic travel dissolves that foundation. It turns human connection into something brittle and delayed, stretched thin across years and light years. There's a philosophical humility hidden in this. Physics is not merely telling us that fast travel is difficult. It's telling us that speed has a social cost, that time is the fabric that holds civilizations together, and you can't distort it without consequences. The universe allows you to outrun your home, but it doesn't allow you to outrun the meaning that home provides. So when people dream about racing between the stars, they're often dreaming about distance while ignoring time. Physics forces us to look at both at once, and what it shows us is sobering. The more extreme the journey, the less human it becomes. In the end, time dilation doesn't just limit interstellar travel. It asks us a question. If moving faster means leaving everything that gives life continuity behind, then maybe the real challenge isn't how far we can go, but how deeply we can understand, protect, and enrich the moment we're already in. By the time you've come to terms with the speed limit of the universe and the way time itself fractures at high velocity, it's tempting to think the remaining obstacles are merely technical. Shield the ship better, harden the hull, add redundancy. But this is where another quiet misunderstanding collapses. Space is often described as empty, as a vast nothing between stars. In reality, it is anything but passive. And the faster you move through it, the more aggressively it reminds you of that fact. Interstellar space is filled with radiation. Not just the gentle glow of distant stars, but high-energy particles accelerated by supernova, black holes, and violent processes scattered across the galaxy. At ordinary speeds, these particles are dangerous but manageable. We already worry about them on the International Space Station. But at relativistic speeds, the rules change. Energy is relative. Motion transforms what was once tolerable into something lethal. A single hydrogen atom drifting between stars doesn't seem threatening. It's about as harmless as matter gets. But when you're moving at a significant fraction of light speed, that atom hits your spacecraft with the energy of a powerful radiation burst. Scale that up to dust grains microscopic, invisible specks, and you're no longer talking about damage. You're talking about destruction. At those speeds, a grain of dust becomes a high-energy projectile, releasing more energy on impact than many explosives. This isn't science fiction exaggeration. It's a direct consequence of relativity. Kinetic energy increases dramatically as velocity approaches light speed. The universe doesn't distinguish between weapon and debris. It only tracks energy, and when you choose to move extremely fast, you convert the medium you're traveling through into a minefield. Shielding seems like the obvious answer until you follow the logic through. To stop high energy radiation and relativistic particles, you need mass. Lots of it, dense material, thick layers, but mass brings inertia, and inertia makes acceleration harder. The more shielding you add, the more energy you need to move the ship. The more energy you need, the closer you push toward the very limits that caused the problem in the first place. It's a feedback loop with no stable solution. And even if you imagine a perfect material, stronger than anything we know, lighter than anything plausible, you still face the fundamental problem of heat. All that energy has to go somewhere. Absorbing radiation and particle impacts means converting their energy into thermal motion. Your shield doesn't just block damage, it heats up. At relativistic speeds, the heating rate becomes extreme. Cooling systems would have to radiate enormous amounts of energy into space. And radiation itself is limited by physical laws. You can't dump heat faster than the universe allows, What's striking here is that none of this requires hostile intent from the cosmos. Space doesn't need to attack you. You create the danger by moving too fast. Speed amplifies every interaction. The universe becomes less forgiving, not because it's cruel, but because energy scales relentlessly. There's a psychological lesson buried in this that goes beyond spacecraft design. We often imagine progress as overcoming resistance. Push harder, go faster, break through, but at a certain point, resistance stops being an obstacle and starts being a warning. The environment isn't something separate from your action, it reacts to it. In the relativistic regime, space itself becomes an active participant in your choices. This forces a re-evaluation of how we think about exploration. The image of a lone ship bravely cutting through a silent void is comforting, but false. The void is alive with particles, fields, and radiation, and your velocity determines how violent that environment appears. Exploration isn't just about where you go. It's about how the universe responds to the way you move through it. And again, this is not a matter of insufficient ingenuity. It's a matter of scaling laws. Physics is telling us that beyond a certain threshold, the cost of speed isn't linear. It explodes. Every additional increment transforms a neutral universe into a hostile one, not metaphorically, literally. So when we talk about interstellar travel as a problem waiting to be solved, we're often ignoring the fact that the universe has already solved it in a different direction. It has made slow processes stable and fast ones punishing. It has favored observation over traversal, signals over ships, understanding over conquest. In that sense, the hostility of space at high speeds is not a dead end. It's a message. It's telling us that the universe is not designed to be crossed recklessly, and that wisdom may lie not in moving faster through it, but in learning how to listen to what it's already telling us. After all the limits we've walked through, the speed wall, the fracture of time, the hostility of space itself, it's tempting to think the final barrier must be something dramatic. Exotic physics, unknown forces, some missing equation we haven't discovered yet. But the most decisive obstacle to interstellar travel is almost disappointingly simple. It's distance, not as a technical inconvenience, but as a fundamental feature of how the universe is structured. We're used to distance being something we shrink with effort, build roads, bridges, aircraft, networks. On Earth, distance feels temporary, but cosmic distance is different. The nearest star system beyond our own is more than 4 light years away. That number sounds abstract until you translate it into meaning. Light, moving at the fastest speed the universe allows, takes over 4 years to make that journey. Not a probe, not a ship, light itself, and that's the closest one. The rest of the galaxy fans out into tens of thousands of light years. Beyond that, other galaxies drift so far away that the expansion of the universe itself begins to pull them beyond our reach. Distance at this scale isn't just large, it's dominant. It defines what can meaningfully interact with what. What's important here is that distance doesn't merely slow us down, it reshapes intention. Even if you imagine perfect engines that flirt with the speed of light, even if you ignore the energy costs, the time dilation, and the radiation hazards, you are still left with journeys that outlast civilizations. A mission to another star is not a chapter in human history. It is a geological process, and this forces an uncomfortable shift in perspective. We like to think of exploration as movement through space, but physics keeps nudging us toward a different interpretation. The universe is astonishingly good at letting information travel. Light, gravity, radio waves all cross vast distances with elegance and reliability. Matter, on the other hand, is slow, heavy, and stubborn. The universe seems optimized for observation, not visitation. That's not an accident. Distance preserves structure. If stars were closer together, planetary systems would be constantly disrupted. Life might never stabilize. If galaxies were packed tighter, gravitational chaos would dominate. The vast separations we now see are not obstacles added after the fact. They are part of what makes a long-lived, intelligible universe possible. There's a philosophical humility in recognizing this. We often project our desires onto the cosmos, assuming it exists to be explored in the same way continents were explored. But the universe is not a frontier in the historical sense. It does not reward expansion with proximity. It rewards patience with insight. Telescopes have shown us this again and again. Without leaving Earth, we've reconstructed the life cycles of stars, the birth of galaxies, and the early moments of the universe itself. We have learned more by staying still and listening carefully than we ever could by trying to rush outward blindly. Distance hasn't stopped understanding, it has shaped it. This reframes what progress actually looks like. Maybe advancement isn't about crossing ever greater spans of space. Maybe it's about increasing the resolution with which we perceive reality, about refining questions rather than escaping limits, about building depth instead of reach. There's also a psychological trap hidden in the dream of interstellar travel. It suggests that meaning lies elsewhere, that fulfillment is waiting at the next star, the next system, the next escape. Physics quietly dismantles that fantasy. It tells us that the universe is vast precisely so that no single place can be treated as disposable. Home matters because leaving it is not trivial. Continuity matters because it cannot be casually restored. Distance enforces responsibility. If you cannot easily leave, you must learn to live wisely where you are. You must understand your environment instead of outrunning it. In that sense, the impossibility of interstellar travel is not a failure of imagination. It is a constraint that forces maturity, and maybe that's the deepest message physics offers here. The universe did not evolve to be conquered step by step. It evolved to be understood layer by layer. The stars are not destinations in the way our myths suggest. They are teachers, broadcasting their stories across space, waiting for minds patient enough to listen. So when you step back and look at the full picture, the conclusion isn't despairing, it's clarifying. The universe hasn't denied us meaning by placing the stars so far away. It has placed meaning right where we already are and dared us to understand it fully before dreaming of elsewhere.